Imagine a world where for a fleeting 5 seconds everything we thought we knew about up and down vanished. Picture this. You're sipping your morning coffee, the birds are chirping, and suddenly, you're weightless, your coffee cup floating mid-air. For those brief 5 seconds, gravity, the invisible force that governs our universe, takes a break. What happens next? Chaos, wonder, a cosmic dance unlike anything we've ever seen. We all know gravity is the force that keeps our feet on the ground. It's the invisible hand that ensures we don't float away into the sky. But what exactly is gravity, and how does it work? To understand this, we need to delve into the history of scientific discovery and the minds that shaped our understanding of this fundamental force. Sir Isaac Newton first cracked this cosmic code, describing gravity as the attraction between any two objects with mass. His groundbreaking work in the 17th century laid the foundation for classical mechanics. Newton's law of universal gravitation states that every point mass attracts every other point mass in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a monumental leap in our understanding of the natural world. The more massive the object, the stronger its gravitational pull. This is why planets orbit the sun and not the other way around. The sun, being the most massive object in our solar system, exerts a powerful gravitational force that keeps the planets in their elliptical orbits. This gravitational dance is a delicate balance of forces that has fascinated scientists for centuries. Then came Einstein, who revolutionized our understanding of gravity with his theory of general relativity. Published in 1915, Einstein's theory proposed a radical new way of looking at gravity. Instead of being a force, gravity was described as a curvature in the fabric of spacetime itself. This was a profound shift from Newtonian mechanics and opened up new avenues of scientific inquiry. Einstein proposed that gravity isn't a force at all, but rather a curvature in the fabric of spacetime caused by mass and energy. Imagine spacetime as a two-dimensional grid. When a massive object like a planet or a star is placed on this grid, it distorts the fabric, creating a well around it. Smaller objects then move along these curves, which we perceive as the force of gravity. Imagine a bowling ball placed on a trampoline, distorting the fabric around it. This is a simple yet powerful analogy to understand how massive objects warp spacetime. The more massive the object, the deeper the well it creates and the stronger the gravitational pull experienced by objects nearby. That's how massive objects warp spacetime, creating what we experience as gravity. This warping effect is not just a theoretical concept. It has been confirmed through various experiments and observations, such as the bending of light around massive objects and the precise movements of planets and stars. Understanding gravity not only helps us comprehend the universe but also paves the way for future discoveries in physics and cosmology. The moment gravity disappears, the effects are instantaneous and dramatic. Everything not firmly secured to the Earth, people, cars, oceans, even the atmosphere, begins to drift upwards. Imagine the feeling of falling upward, a sensation both exhilarating and terrifying. Buildings rooted to the ground would remain, but anything inside them would start to float. The first second becomes a chaotic ballet of objects in free fall. As we reach the second tick of our gravity-free clock, the Earth's rotation comes into play. Without gravity to hold it together, our planet's spin would send everything flying eastward at hundreds of miles per hour. Imagine a merry-go-round suddenly stopping. That's the kind of force we're talking about. Oceans would surge, creating monstrous tsunamis, while the air itself would thin, causing enormous pressure changes. Section 5. The Return of the King. Gravity strikes back. After 5 long seconds, gravity returns with a vengeance. Everything that was once gently floating is now hurtling back towards the Earth. Remember that feeling of falling upward? Now imagine that sensation amplified as everything crashes back down with the same force it initially floated up with. Buildings crumble, trees snap, and the planet experiences a global earthquake of unimaginable scale. Section 6. Cosmic Ballet. The Moon's Great Escape and Earth's New Path. The consequences of our 5-second gravity holiday extend beyond Earth's atmosphere. The Moon, no longer tethered by Earth's gravitational pull, would embark on a new trajectory, potentially escaping Earth's orbit altogether. Earth itself, now free from the Sun's gravitational grip for a brief period, would also deviate from its orbit, potentially altering our climate and seasons for centuries to come. Section 7. Time and space, more than meets the eye. Einstein's theory of general relativity tells us that gravity affects not just objects but also time itself. The stronger the gravitational field, the slower time passes. During our 5-second gravity lapse, time would actually speed up, albeit infinitesimally. While we might not notice this minuscule time warp, our GPS systems, which rely on precise time measurements, would be thrown into disarray. This highlights the intricate connection between gravity, time, and our technological infrastructure. Section 8. The quantum realm, where gravity plays dice. The bizarre world of quantum mechanics, where particles can be in multiple states at once, adds another layer of complexity to our gravity-free scenario. In this realm, particles don't follow the conventional rules of physics that we observe in our everyday lives. Instead, they exist in a state of superposition, where they can be in multiple places or states simultaneously. This phenomenon challenges our understanding of reality and forces us to rethink the very nature of existence. Quantum entanglement, the spooky action at a distance where two entangled particles can influence each other instantaneously, regardless of distance, could be affected by the absence of gravity. This entanglement means that the state of one particle is directly connected to the state of another, no matter how far apart they are. It's as if the particles share a mysterious, invisible bond that transcends space and time. But what happens to this bond in a universe without gravity? How would this entanglement be impacted? Would the lack of gravitational forces disrupt this delicate connection, or would it remain unaffected? These questions push the boundaries of our current scientific understanding and open up new avenues of exploration. Scientists are constantly probing these mysteries, trying to uncover the hidden mechanisms that govern the quantum world. Would the fabric of reality as we know it unravel? The fabric of spacetime, a concept introduced by Einstein's theory of general relativity, is intertwined with gravity. If gravity were to vanish, would the very structure of the universe begin to fall apart? This question is not just theoretical, it has profound implications for our understanding of the cosmos and the fundamental laws that govern it. These are questions that continue to baffle physicists. Despite decades of research and countless experiments, the quantum realm remains one of the most enigmatic and perplexing areas of science. Every discovery leads to new questions, and the deeper we delve, the more we realize how much we have yet to understand. The quest to unravel these mysteries is ongoing, and each step brings us closer to a more complete picture of the universe. Section 9. Gravity's Grip, a universe of wonder. Imagine a universe where gravity, the invisible force that binds us all, suddenly took a 5-second break. What would happen? This thought experiment, while purely hypothetical, underscores the profound influence gravity exerts on every aspect of our existence. Picture objects floating away, people lifting off the ground, and natural phenomena going haywire. Gravity is not just a force, it's the glue that holds the cosmos together. Without it, the very fabric of our reality would unravel. From the grand dance of planets orbiting the sun to the intricate workings of an atom, gravity shapes the universe as we know it. It governs the motion of celestial bodies, dictates the structure of galaxies, and even influences the behavior of subatomic particles. It's a force we often take for granted, yet its absence, even for a mere 5 seconds, would have mind-blowing consequences. Imagine astronauts in space, suddenly untethered, drifting aimlessly. Or consider the oceans momentarily freed from gravity's grip, causing unimaginable chaos. So, the next time you feel gravity's pull, take a moment to appreciate this fundamental force that holds our universe together. It's not just about keeping us grounded, it's about maintaining the delicate balance that allows life to thrive. What other consequences can you imagine if gravity took a 5-second break? Would buildings remain standing? Would our atmosphere stay intact? The possibilities are as endless as the universe itself. Share your thoughts and let's explore the wonders of the universe together. Engage in discussions, spark your imagination, and delve into the mysteries that make our cosmos so fascinating. The universe is a vast expanse of wonders, and gravity is just one of its many marvels. On a cosmic scale, gravity's influence is even more profound. Near a black hole, gravity is so intense that time dilation becomes extreme, slowing time near the event horizon to almost a standstill compared to an observer far away. If gravity were to disappear, black holes would cease to exist as space-time collapses into a flat state, and the immense time dilation effects near black holes would instantly vanish. gravity also counters the universe's expansion at local scales, such as galaxies bound by gravity resisting flying apart. Without gravity, the expansion rate could increase drastically, stretching spacetime even faster. The cosmic microwave background, a remnant of the early universe, is distorted by gravitational fields. If gravity vanishes, these distortions, known as gravitational lensing, would disappear. Some fringe theories even suggest that gravity is tied to the forward flow of time. Could time flow backward if gravity vanishes? Theoretical considerations like these push the boundaries of our understanding and ignite our curiosity about the universe.